Hi everyone. So in this video we start a discussion of long short-term memory cells, which are basically the basis for LSTM layers that have multiple of these units or of these cells. And this is kind of the most commonly used type of what's known as gated recurrent neural networks. And the idea of gates is basically to let the network learn based on the data seen so far to decide when to forget or keep the accumulated information, right? So that decision, and this is basically a follow-up of the discussion we had on skip connections and leaky units, right? So preferably we want this to be dynamic, but of course it will add complexity to learning. So let's see from the discussion here, like after we finish the description of LSTM, let's see reflect on the relationship of this to skip connections and leaky units, and in general capturing multiple time scales to easily capture long-term temporal correlations. So an LSTM cell has 3 gates, right? An input gate, a forget gate, and an output gate. So an input gate controls basically whether to allow the new input in or no. And if yes, by how much? So by how much would we allow the new input corresponding to the current time step in and let it affect the state, the current state. The forget gate controls by how much we are keeping information from the previous state. And the output gate decides by how much are we allowing the output at the current time step, right? So the output gate, it can be a little bit not straightforward to understand the functionality of the output gate, and I'll defer that to the next video. So here, let's focus on the input gate, forget gate, and the input nonlinearity. So we have as input x of t and h of t minus 1, the previous state, right, as input. And we can apply a nonlinearity to that input, okay, as if we do normally without having gates. And then we have an input gate that controls basically how much we are letting that input after the nonlinearity, how much will it affect the current state, right? So here we have the input nonlinearity, then multiplication by the output of the input gate. The input gate itself can have as input the current input, the current time x of t, as well as the previous state. Because the previous state basically summarizes or has a summary or a reservoir of information about the inputs x of 1 up to x of t minus 1. So we use all that to control by how much we are opening the gate. And then the current state has a delay, right? So this is a delay by one time step, and then a multiplication by the output of the forget gate to determine how much we are keeping the previous state, how much we are letting in affect the current state, right? And then next time we'll discuss the output gate and how could that be useful, okay? So this is an LSTM cell. Let's take a closer look at the equations. So let's see the forget gate. The output of the forget gate, let's call it Fi at time step t, is basically a sigmoid applied on bias values, which are learnable parameters. Let's call them Bi of f, right? So I is the forget gate for LSTM unit I. And this is the bias for the forget gate for LSTM unit I. And then you sum over the input weights Uij. So this is the weight of the forget gate of LSTM unit I with respect to the input with index j at time, and then we multiply by the value of that input at time t, right? So we could have an input vector. X here could be a vector, right? H could be a vector. And the LSTM units are also a vector. We have multiple of them. So this is the forget gate for LSTM unit I at time step t. And we apply a sigmoid to the bias of the forget gate of LSTM unit I. Then we sum over all inputs j. And then we have weights connecting LSTM unit I to the input number j. We multiply by the input number j at time step t. And then we have a sum of the weights W of LSTM unit I to the state J, right? And then we Hj of t minus 1. And the lengths of the H vector and the X vector could be different. So the ranges for the J in this summation and the J in this summation could be different. And we apply a sigmoid. So in general, we apply a sigmoid to all the gates, not necessarily to the input nonlinearity, but to all the gates, right? Now, this is justified only by empirical results so far. So it's kind of an open research problem. Why would you use a sigmoid as hidden layer activation for the gates? But one, like just a sanity check, sigmoid outputs 0 to 1, and the gates decide on a weight between 0 to 1. 0 means you forget or the gate is closed. 1 means you allow or the gate is open. Okay? So all the gates are using sigmoid, but as a reflection exercise, you should think of all the problems with sigmoid when you don't apply something that undoes the exponential, like the cross entropy loss, right? So here the sigmoid can saturate easily, right? But you should also think about this is a sigmoid for the gate, right? So how frequent, you should think about how frequent you would need to update these gates, right? So the gate doesn't determine the whole learning process, but the gate determines the dynamics of the learning. So it determines how the function works, how the learning function works in terms of capturing temporal correlations. So you should think of saturation, meaning the gate will not change, the state of the gate will not change, right? Easily. So so it's not clear whether this is something needed or something bad, actually, right? So that's a good reflection exercise, I think. The input gate has a similar form, so we call it Gi of t, and the input gate is a sigmoid applied to the input biases plus weights connected to the inputs plus weights connected to the previous state. Now updating the cell state, Si of t equal Fi of t times Si of t minus 1, so this is the forget gate output, times the previous state value, plus Gi of t, which is the output of the input gate, times an input nonlinearity, not necessarily a sigmoid, right? So this is important to note. Sigmoid has been successful with the gate nonlinearities, not necessarily for the input nonlinearity. And then a bias value for the state plus weights connected to the input plus weights connected to the previous state, right? So next time we'll start discussing the output gate and the implications of arranging multiple LSTM units in one layer, and the connection between LSTM units and skip connections and leaky units that we discussed in previous video. Thank you.